CMB whispers, the cold hole that shouldn't be. You don't argue with the afterglow lightly. The cosmic microwave background is the oldest photograph we have. Grainy, yes, but honest. If something toys with photons on their way to us, the picture records it as a faint temperature bruise. That's the late-time Integrated Sachs-Wolfe ISW effect. As dark energy stretches space, gravitational wells and hills evolve, and CMB photons gain or lose a sliver of energy crossing them. A supervoid should make a tiny, cool patch. Tiny is the key word. So people did the careful thing. They took maps from WMAP and Planck and cross-correlated them with catalogs of voids. Nothing spiritual about it, just statistics. Stack hundreds of void positions, average the microwave temperature around each, and any random blotches cancel. What's left, if anything, is the collective whisper of underdensities dimming the afterglow. Over Boötes, the whisper sounded like a hush. The stacked profiles showed a dip, not a dramatic bite, but in several analyses slightly deeper and more coherent than conservative Lambda-CDM forecasts prefer. You could see the outline of the basin in microwave temperature, a few microkelvin down from its surroundings, aligning a little too well with where galaxy counts thinned. When analysts rotated the sky or scrambled the void positions, the signal faded. Put the voids back where they belonged, the dip returned. That's when arguments got loud. Foregrounds can lie. Dust, synchrotron noise, the Milky Way's messy halo, cleaning those out is half art, half discipline. Teams ran different masks, different component separation algorithms, different sky cuts. They worried about overfitting, underfitting, confirmation bias. One group saw the dip shrink with stricter cuts. Another saw it survive when they limited themselves to the cleanest patches. The debate was blunt. Is this physics or a calibration ghost? Meanwhile, the simple expectation wouldn't budge. Under Lambda-CDM, the ISW signal from a void that size should be small. Not zero, but small. The measured depression looked a notch too large, and in some analyses, a notch too coherent, as if the gravitational potential inside Boötes had evolved more than its matter content alone would suggest. Shallower wells, yes, but shallower by how much? Here's where a human moment cut through the math. An analyst confessed later that they spent weeks trying to kill the signal, change the filter, change the catalog, subtract the dipole, the quadrupole, the kitchen sink. The more they tried to erase it, the more it thinned but stayed put, like pencils still faintly visible after an eraser smears the paper. I'm not saying I believe it, they told a colleague. I'm saying it won't leave. What nobody knew at the time was whether Boötes was special or the tip of a pattern. Some stacks used many voids and got a modest dip. Focus on the biggest basins, the hint grew. That made sense. Bigger emptiness, bigger effect. But the amplitude remained awkward. Theoretical curves could be coaxed to meet it with creative assumptions, yet they didn't arrive there comfortably. And comfortable matters when the data you're comparing against is our gold standard for the early universe. The stakes were clear. If the afterglow is quieter across Boötes, either we've misread the foregrounds, miscounted the void, or something about the way information, gravitational memory, propagates through that region has changed. Because the ISW effect isn't just about matter, it's about how the potential landscape decays as dark energy drives expansion. Fewer galaxies alone shouldn't mute the echo more than the models allow. A muted echo hints that the landscape inside the basin is evolving with fewer updates than expected. Now stack that with the local tracers going missing, the dwarfs that don't show, the background fluctuations that flat. Light is failing two ways, fewer sources and a quieter journey. That's not a coincidence you wave away with a better flat field. It's a through line. If reality renders, where information changes, a region with fewer dynamical changes would offer fewer chances for photons to pick up that late-time energy tweak. The ISW hush becomes a symptom of sparse updates. Critics pushed back hard. They pointed to simulation-based void definitions that dilute the stacked signal. Change how you find voids, change the amplitude. They reminded everyone that the CMB is a jungle of correlated noise, where clever statistics can find faces in leaves. And they were right to be skeptical. This is where careers spend themselves prudently. But each new round of data kept a version of the dip alive. Different catalogs, different cleaning, the outline remained visible enough to keep the fight going. Even when the numbers retreated toward Lambda-CDM's comfort zone, the alignment itself, microwave coolness draped over a mapped emptiness, refused to break. Here's the unsettling part. If the afterglow is the universe's memory, Boötes reads like a smudge, a place where the record is thin, not just the matter. The cold spot language isn't perfect. We're not claiming the famous anomaly lives here. We're saying the same physics that can make a spot colder than it should be appears to act more strongly over this basin than tidy models expect. And that tees up a harder question. If ancient light is quieter there, what's killing the echo? And why do our local tracers, the dwarfs and the dust and the faint fuzz, vanish along the same lines? Either every pipeline in astronomy learned the same bad habit at once, or the void isn't just less. It's less communicative, less willing to pass along change. To answer that, we have to look not just for missing light, but for where the sky stops bothering to whisper at all. That takes us from the afterglow to the missing glow, the starlight that should be there and is. The missing light problem. We went looking for galaxies and found an absence. Fine, voids do that. But then we went looking for the glow that galaxies leave behind, the low, stubborn smear of starlight that clings to the edges of structure, and the absence stared back. Start with the most forgiving targets, low surface brightness dwarfs. They're the background singers of the cosmic web, quiet everywhere, hard to spot unless you're patient. Standard void studies expect a suppressed but non-zero dwarf population inside even deep voids. Filaments and subvoids usually thread some through. So teams cleared the usual hurdles: dark time, deep exposures, stacked frames. They pushed well below the brightness where dwarfs hide. The counts didn't just dip, they stalled. Survey after survey, when sightlines crossed the basin, the histogram tails that should rise gently with faint galaxies stayed flat. Spectral lines that normally poke up like fence posts, H-alpha, O-Roman 2, faded earlier than the noise model predicted. The sky background, which usually wobbles with unresolved sources, looked ironed. Not smoother because of better instruments, smoother because there was less there to roughen it. A grad student told me about a night they'll never forget. They stacked 100 cutouts from a region just inside the rim, aligning by stars, calibrating flats to within a hair. The combined image should have teased out a population of near-invisible dwarfs. When the stack rendered, it was respectable, clean, featureless. They did the ritual rotate stamps, mirror them, randomize positions to test the pipeline. The blankness cared about none of it. At 3 a.m., they wrote in their lab notebook, "Either I broke the code or the void is doing it for me." Skeptics circled the instrumentation. Was the detection threshold truly below where dwarfs live? Teams injected fake galaxies into the raw frames, spanning sizes and brightnesses, then ran the pipeline blind. The software recovered them at the expected rates. Completeness curves looked great, outside the void and by design inside. But when they replaced fake galaxies with the real sky inside the basin, the catalogs thinned anyway. The simulation said you'd see them. The universe said there aren't any to see. Meanwhile, spectroscopy added a second kind of quiet. In fields bordering the basin, the distribution of equivalent widths, how bold your emission lines are, tapers as usual. Inside, the taper steepens like someone turned down the gas on star formation long ago. It wasn't just fewer galaxies. It was galaxies, if present, that behaved like they'd aged out of noise-making. The chemical clues matched. Metallicities plateaued near the rim, then stopped evolving inward. Dust temperatures, where measurable, sagged below the fit-U-D draw from denser regions. It formed a picture of a population that either never built up or got reset to a simpler state. The pushback pivoted to selection. Maybe the dwarfs are so diffuse they blur into the background and never get flagged. Maybe the void's backgrounds are subtly different, airglow variations, zodiacal light tricking our thresholds. Observers responded with ugly tests, Point at control fields with identical ecliptic latitudes, match seeing, humidity, moon angle. Results held. Others changed the game entirely. Use radio to fish for HI gas without caring about starlight. Void interiors had gas spore signatures compared to expectations. If there were hidden dwarfs, they weren't hiding behind neutral hydrogen in comfortable numbers. Here's where the story bent toward intent, even if nobody claimed agency. The absence wasn't random. Low information structures, the small, dim, slowly changing, disappeared first. High information hubs on the rim looked normal. In between, the feathery bridges that should betray the web were curtailed. The pattern matched a rule, not a mess. If you were designing a system to conserve effort, you'd keep the busy parts and cull the quiet ones. That idea sat like a metaphor until it started making testable predictions. If culling prefers low complexity, then pushing below the usual surface brightness limits should not eventually reveal a buried population. You could throw time at the void and get nothing back because nothing passed the rule. Teams did throw time. The void threw back silence. Another angle, background fluctuations. Even a blank field carries speckle from innumerable unresolved sources. You measure it by the pixel-to-pixel variance after subtracting known foregrounds. Across the basin, that variance flattened. The statistical snow thinned. It's the kind of metric that doesn't care about galaxy catalogs. It cares about how noisy the sky is at baseline. Less noise means fewer contributors. Fewer contributors means fewer chances for the universe to surprise your detector. All the while, proposals drifted away from the basin. Telescope time committees read Boötes and saw risk, long hours chasing nulls. People learned to bury the void in the control sample paragraph. That reflex turned into a self-fulfilling subtraction. Observational attention, like starlight, avoids low payoffs. The absence deepened behind policy as well as physics. There was a moment in a hallway when a cosmologist, dog-tired, said, "I hate the rendering metaphor. It's sticky, but it keeps predicting where we fail to find things." They weren't endorsing simulation talk. They were admitting a pattern recognition problem. The data clusters around a story where the universe allocates change unevenly. And there's the crux. The ISW hush told us the Afterglow picks up fewer updates crossing Boötes. The missing light tells us there are fewer updates to pick up. Two quiets, same address. If a renderer skips frames where little changes, this is what the sky would look like. Sources sparse, dwarfs culled, fluctuations ironed. Cleaned by what or by whom? We still needed edges, rules, timing. But before we went hunting for boundaries, we had to ask a harder question. Are we mistaking deletion for subtle gravity or gravity for efficient deletion? The next tests would push on that seam. The rendering hypothesis, when the universe stops drawing. Here's the idea people hate saying out loud because it sounds like science fiction. What if the universe renders detail where information changes fastest and lets the rest blur? Not a programmer in the sky, a rule, a budgeting of complexity. The metaphor grew in the cracks between what gravity predicted and what Boötes delivered. Start with cost. Physics already has budgets. Entropy bounds tell us there's a maximum information content in any region. The holographic principle sketches it on the boundary. If there's a ceiling, there may also be priorities. Systems under constraints triage. They keep the high gradient stuff because that's where predictions are fragile. Mergers, starbursts, shocks, the noisy hubs on the web. Low surface brightness dwarfs drifting quietly inside a supervoid. Low return on detail. If something has to give, you let those fade first. Translate that into a rule of thumb, not a law. Maintain resolution where Kolmogorov of complexity, true descriptive content, runs high, and compress where updates are rare. It looks like ruthless lossless compression at cluster cores and lossy compression in empty corridors. The ISW hush over Boötes says late-time gravitational updates run thin there. The missing light says low information contributors are absent to begin with. Two lines cross on the same graph. Now the counterargument arrives armed. Lambda-CDM can grow big, rare voids. N-body runs spit out basins hundreds of millions of light years across. That's true. But even the largest simulated voids have texture, subvoids, tendrils, a residual dwarf population that refuses to vanish. Observations of Boötes keep painting a cleaner interior than those basins predict. So the rendering frame doesn't replace gravity, it rides on top of it. Gravity hollows the basin. And information, heuristic strips out what's left of the quiet parts. What would that look like in practice? You'd expect thresholds. Below a certain surface brightness or dynamical activity, structures stop earning persistence. That creates selection-like effects in the physical sky, not just our catalogs. Push deeper exposures and you don't cross a fog bank into hidden dwarfs. You hit a wall. Try a different messenger and you might recover some scaffolding, because non-photonic channels don't depend on luminous updates in the same way. That's exactly where neutrinos and gravitational murmurs become interesting later in the story. But first, keep the speculation dressed in physics clothes. Holographic bounds set an area-based information limit. Dark energy accelerates expansion, stretching potentials and reducing late-time structure growth. Combine the two and you get a universe that's both bounded in information and increasingly bored in its emptiest halls. If you were going to save on the cost of representing everything at full fidelity, you'd shave the boring hall first. Boötes is a cathedral of boredom. Here's a human moment that made this metaphor sticky. A cosmologist scrawled a sketch on a whiteboard, intensity of updates on one axis, observational recovery on the other. Data points from clusters hug the high corner, fast updates, easy recovery. The void interior points slumped low. They drew a diagonal line and wrote, "Culling plane." Nobody claimed a mechanism. They just noted the divide sorted the archive better than some equations did. If the heuristic is real, it should leave edges. Not smooth gradients, but places where the rule flips. Outside the rim, the web insists on detail. Inside, the rule relaxes and culls low-complexity contributors. You wouldn't need an absolute void, just a step in how much gets to stick around. That's why the obsession with step functions at the boundary matters. It's not aesthetics, it's governance, a sign that something besides smooth gravity is drawing the map. Objections keep us honest. You're anthropomorphizing physics, a reviewer wrote. Fair. So swap the metaphor for a test. If there's a culling plane, then multiple tracers should register the same edge. Galaxy counts, weak lensing shear, even the ISW contrast, all bending together across the same contour. Selection effects must be hammered with rotated masks, synthetic skies, and alternative void definitions. If the edge survives those gauntlets, then the metaphor graduates to a diagnostic. Another test, time. If the renderer skips where updates are rare, you should see fewer transients per volume inside the basin. Supernovae, AGN flickers, then density alone explains. Rates adjusted for underdensity should still underperform. That's a clock test we can run because the ISW itself is a kind of watch, sensitive to how potentials evolve. If both the transient clock and the ISW clock tick slowly inside Boötes, the culling frame predicts coherence between them. And a third, cross-messenger stubbornness. If photons are our change carriers and they grow quiet across the basin, neutrinos and gravity waves shouldn't fade in lockstep. They couple differently. A renderer that prioritizes dynamical novelty in luminous matter will starve optical surveys first, not the neutrino background. So when we later see hints that non-photonic channels preserve scaffolding where light fails, that's not a flourish. It's a forecast. None of this requires intent. A rule can emerge from deeper physics just like flow patterns emerge from water without a water god. But the rendering hypothesis forces us to ask a daring question. Are we bumping into an information principle we haven't written down yet? One that treats reality as a ledger and makes deletions where the balance sheet barely changes. If it's a rule, it should draw a line. So we went hunting for knives in the dark, sharp boundaries, knives in the dark, sky looking for bothering edges with detail. We went looking for a slope and prayed we wouldn't find a cliff. If gravity alone sculpts the basin, galaxy counts should fade like dusk, gradual, patient. A cliff would be something else, a cutoff that looks like a rule. So we trace the rim. Pick a great circle that skims the boundary, lay down apertures like stepping stones and count. Bright galaxies, dwarfs, anything with a trustworthy redshift. Then slide the whole chain inward by a few arc minutes and count again. Outside the basin, the web behaves, counts swell, filaments cross the field, the histograms breathe. Step across the putative boundary and in some slices the numbers don't dim, they drop. Not to zero, to different. It wasn't one catalog. Teams ran SDSS, DES, deeper pointings. They cut by surface brightness to dodge bias, by color to isolate star-forming spillover, by photometric redshift to tag likely interlopers. The shape of the transition flexed, but a pattern kept resurfacing. A kink you could draw your finger over, where counts changed faster than density gradients alone predicted. When skeptics rotated the footprint by 90 degrees, same masks, same stars, the kink softened or vanished. Snap it back to the void's real contour, it sharpened. Annoying because that's what you'd see if an edge were real and your systematics were trying to imitate it. Weak lensing offered a second blade. Map the shear, how background galaxies get stretched by foreground mass, and you get a pressure-sensing skin for the cosmic web. Near the rim, shear profiles should flatten as you step into an underdensity, but they shouldn't pancake. In the Boötes direction, some reconstructions showed the flattening happen a hair too quickly, like a rug pulled snug at a doorway. Not a gaping lensing deficit. Voids don't lens like clusters, but a too crisp transition in the gradient. You don't bet your thesis on that alone. You put it next to the counts and ask why they rhyme. Meanwhile, CMB maps drew their own contour. Take the ISW contrast, the microwave dip we argued about, and watch how it changes as you march across the boundary. In stacks aligned to the basin's geometry, the temperature profile traced an edge that tracked the same sky where galaxy counts kinked. 3 tracers counts, shear, microwave hush, bending across roughly the same line. It's the kind of triangulation that makes you breathe slower. Then came the bleeding obvious. Masks can fake everything. Bright stars burn holes in catalogs, satellite trails scar exposures, chip gaps hide in the seams. Committees convene to demolish the cliff, rotate masks, inject synthetic galaxies, plant artificial shear into the raw and see if recovery invents edges. The edges wobbled under the assault as they should if some of the signal is wishful, but they didn't dissolve. When the void was redefined by an independent finder, density ridges inverted into basins, not by galaxy counts but by a topological spine. The rim shifted a few degrees. The kink moved with it. I remember a night on the mountain when we were timing the step. We had half an hour before twilight and one more strip to scan along a path that crawled across the rim. The console clock felt like a dare. We squeezed in the exposures, watching seeing worsen by the minute, and hit readout on the final frame as the dome took on that pre-dawn cold. Back at the laptop, the quick and dirty counts plotted into a line with a bruise, a sharp break right where the schedule said it might be. We shouldn't have trusted a plot made on no sleep. We did anyway, just long enough to write knife on a sticky note and slap it to the monitor. Back in daylight, statisticians asked the only question that matters: how steep is steep? Fit a logistic curve, a smooth step to the counts across the boundary. Let the midpoint and width float. The best fits wanted a transition a few tens of megaparsecs wide in comoving units, narrow compared to the basin's radius. Not infinitely sharp, not a wall, but more like a gasket, the same sense you get when a system changes mode. Inside, low information structures underperform. Outside, the web asserts itself. Across the gasket, rules switch. Here, where caution saved us from ourselves. Selection effects can mimic a gasket, especially if surveyed depth changes with air mass or galactic latitude. So we sliced the sky by ecliptic coordinates, kept only regions with uniform exposure time and reran the fits. The edge survived in the cleanest halves. That doesn't end the argument. It keeps it open. What nobody knew, standing at those plots, was which enforcer wrote the line. Gravity, with a profile sharper than our simulations admit, or an information rule that treats the rim like a culling plane, sparing high-entropy hubs just outside while downranking low-complexity interiors. The counts can't answer motive. They can only point to behavior. But behavior stacks. Shear flattens too quickly. ISW contrast bends along the same trace. Dwarf-sensitive catalogs show the steepest kink because they're sampling exactly the structures a culling rule would drop first. Put those together, and the edge stops feeling like a cartographer's error and starts feeling like governance. Edges suggest someone or something keeps the boundary. Gravity would paint a gradient. A rule draws a line. If the sky carries a line, it should also carry a failure of gravity's usual tools to explain it. And that's where we went next, testing whether curvature alone can account for a basin that looks this clean, or whether our knives have cut into new physics.